Hello everyone. Today we are going to explore the Purdue model, which serves as the architectural backbone for industrial cybersecurity. So today is Sunday. I have got some time. So let's grab your coffee or snacks as this video is going to be a bit long. So the Purdue model is very crucial in understanding how modern industrial automation environment works, such as manufacturing plants and critical infrastructure are structured for both efficiency and security. This framework not only describes how control systems and business systems are separated, but also how these layers interact and when cybersecurity measures must be applied. By mastering the Purdue model, you gain insight into why industrial networks are designed the way they are and how targeted security strategies can protect operations from emerging cyber threats. Let's start our journey by understanding what Purdue model is and why it was created and how it underpins industrial automation and security across a wide range of industries. For the foundation of today's discussion, let's define what the Purdue model actually is. The Purdue model, formerly known as Purdue Enterprise Reference Architecture or PERA, PERA, is a foundational framework that has been adopted worldwide as the standard for structuring industrial automation and cybersecurity systems. This model was created to address a fundamental challenge in modern industry. How do we securely and efficiently connect the operational technology that runs our factories, the robots, sensors, and controllers on the factory floor, with the information technology system that handles business operation and data? Now, this Purdue model solves this challenge through a layered approach. It organizes industrial system into multiple tiers, each responsible for different levels of operation, from physical, machinery, and robots, like the ones you see on screen, up to the high-level enterprise IT systems and cloud applications. With the rise of Industry 4.0, this framework is more important than ever. As manufacturers seek to connect formerly isolated systems to enterprise network and cloud platforms, the Purdue model helps ensure these integrations are secure, manageable, and reliable, enabling both innovation and protection in digital manufacturing environment. Now let's break down this Purdue model into six distinct layers, each playing a unique and critical role within industrial system. So let's start with level 0, which is the physical process. This is the foundational layer consisting of the actual field devices, sensors, actuators, pumps, motors, and valves that directly interact with and control the industrial process itself. Intelligent control devices. The layer just above include programmable logic controllers or PLCs and remote terminal units called RTUs. These devices are responsible for processing input from level 0, executing control logic, and sending out commands back to the physical equipment. Then comes the level 2. Here we see supervisory control systems such as SCADA, DCS, and HMIs. These allow human operator to monitor, visualize, and control processes, bridging the gap between real-time control and higher level management. Level 3 is site operation. This layer handles complex manufacturing operations. Systems like the Manufacturing Execution System or MES are responsible for production planning, quality control, and site level data collection, essential for optimizing plant performance. Level 3.5, the DMZ buffer zone. Unique to security focused architecture, this critical layer sits between plant, network, and business networks. It uses proxies and data diodes to limit and filter communication, forming a strict barrier that protects operational technology from IT based threats. Level 4 and 5 are the enterprise systems. Finally, the topmost layer represent business logistic and enterprise IT systems, including ERP, CRMs, analytics, email, and all corporate IT functions. These systems focus on business administration, planning, and organization wide function, but must be carefully segregated from plant operation. By structuring industrial system into these functionality distinct layers, the Purdue model ensures both operational efficiency and strong security, helping keep critical process safe, reliable, and resilient. Let's start from the very foundation of the Purdue model, level 0, the physical process layer. This layer represents the actual industry machinery and field devices at the heart of any manufacturing operation. Here we find the motors that power equipments, valves that regulate the flow of liquid or gases, pumps that move materials, and sensors that measures key variables like temperature, pressure, flow rate, and even chemical composition. These aren't just any devices. They are designed to operate in rugged, often harsh industrial environments, sometimes exposed to extreme temperature, vibration, dust, or moisture. Because of this, reliability is absolutely crucial. Level 0 devices must work continuously without failure to keep the entire operation running smoothly and safely. Importantly, these devices form the vital interface between the physical world of material transformation and the digital realm of control systems. Without sensors, you wouldn't know what's happening inside your production line, and without actuators, you couldn't respond when change is needed. Today, even these foundational devices are becoming smarter. Many incorporate diagnostic and self monitoring features, support predictive maintenance, and allow for improved communication with higher level systems. This sets the stage for Industry 4.0, where even the most basic element of industrial processes are digitalized, connected, and optimized. In summary, level 0 is where digital ambition meet industrial reality, turning electronic signal into tangible action on the shop floor. Moving up to the Purdue model, let's look at level 1 and 2, which are all about control and supervision between the industrial systems. Level 1 is intelligent control. At this level, we have devices like the PLCs and the RTUs, which we discussed previously. These devices are the brain of real time control logic. They constantly receive data from the field sensor and execute automated instructions. For example, if a temperature sensor signal overheats, the PLC can immediately activate a cooling system. This automation isn't just about convenience, it's essential for running industrial operations safely and efficiently. PLCs and RTOs guarantee that sensor, actuator, and safety interlocks are all working in perfect harmony, performing necessary tasks in milliseconds. Level 2 is supervisory system. This is where the systems like the SCADA, supervisory control and data acquisition, and HMI, human machine interface, come into play. These tools let plant operators monitor and control entire production processes with ease. Through SCADA and HMI, operators gain real time visibility into what's happening on the plant floor. They can review historical data, respond to alarms, and even intervene manually if a process needs adjustment. Think of this as the mission control for plant operation, providing comprehensive oversight and ensuring everything stays on track. Together, level 1 and 2 ensure that both automated control and human oversight combine to keep industrial operation precise, reliable, and adaptable. Now we reach level 3 of the Purdue model, manufacturing operation management. This layer is all about bridging the gap between the real time operation of the factory floor and the strategic needs of the business. At this level, we see systems designed to optimize production efficiency, coordinate activities across the entire plant, and maintain rigorous quality standards. The first key system is the Manufacturing Execution System, or MES. Think of MES as the command center for production. It coordinates schedules, tracks work orders, manages batch processes, and ensure every step meets quality requirement. MES platforms offer real-time visibility into how production is performing, allowing teams to make quick decisions and respond rapidly to changing situations. Next are data historians. These are specialized databases that gather and analyze vast amount of process data over the time. With with data historians, manufacturing teams can identify trend, optimize performance, and generate reports for regulatory compliance, turning raw material, informational, or operational data into valuable business intelligence. Third, we have quality management system. These platforms monitor product quality parameters, coordinate rigorous testing procedures, and ensure that everything produced meets both industry and regulatory standards. In highly regulated industry like pharmaceuticals or automotive, these systems are absolutely essential for maintaining customer trust and market access. Overall, level 3 ensures manufacturing is not just automated, but consistently optimized and aligned with broader business goals, forming a critical bridge in the connected data driven factory of today. As we move beyond core manufacturing operations, we reach one of the most important and innovative layer of the Purdue model, level 3.5, the demilitarized zone or the DMZ. The DMZ is all about security. Think of it as a highly controlled buffer zone that sits between the plant's operational technology network, the heart of industrial process, and the business focused information technology systems of the enterprise. Its job is to ensure that necessary data can flow between the business and factory floor, but in a highly filtered and protected manner. Within the DMZ, we use a combination of security proxies, data diodes, and application layer gateways to rigorously filter, inspect, and control all data traffic. The layer is crucial for enabling business integration, think remote management and analytics, without exposing critical control system to unauthorized access or potential cyber threats. Modern DMZ architectures go even further. They incorporate advanced threat detection, data validation, and protocol translation, ensuring that only legitimate, clean, sanitized data can pass through. This approach not only prevents cyber attacks from jumping between IT and OT, but also enhances compliance with both security practices and regulatory standards. Ultimately, the DMZ is the front line of defense in the connected factory, enabling productivity while guarding the gates between the two different worlds. Finally, we reach the top layer of the Purdue model, level 4 and 5, which focuses on business and enterprise systems. So level 4 is business logistics. This is where we find core business platforms like the enterprise resource planning or the ERP, customer relationship management CRM, and supply chain management systems. These systems are responsible for handling business operations from financial management and resource planning to tracking customer interactions and managing workflows through the organization. In essence, level 4 brings together all the data and activities needed to keep the business side of manufacturing running smoothly and strategically. Now, level 5 is corporate IT. This is the realm of traditional information technology, covering everything from company email and file server to business intelligence tool and cloud based enterprise services. Level 5 connects the corporate office, C suites, and business analytics, giving them access to the high level data and analytics they need to make informed strategic decisions. At this level, at these levels, the focus shifts from day to day production to company wide decisions making and optimization. The key challenge and the opportunity is securely and efficiently integrating manufacturing data with these business systems. This actually helps the leadership to have information required for growth, compliance, and innovation, but always with strict, well defined boundaries. So, in summary, level 4 and level 5 ensure that manufacturing is tightly aligned with broader business strategy, setting the stage for success in digital economy. Now, as we conclude our overview, let's highlight why Purdue model is so vital in today's industrial cybersecurity and operations. First, it provides an enhanced security posture by creating natural boundaries within the organization. These boundaries help prevent cyber threats from moving laterally between operation technology and business network. Each layer can implement its own specialized security controls, significantly limiting the impact of any potential attack. Second, it enables safe digital information. As industry pursue Industry 4.0 initiatives and IT/OT convergence, the Purdue model's layered approach makes it possible to adopt new technologies and integrate systems without compromising operational security. This structure supports innovation while managing risk. Third, the Purdue model is the benchmark for industry standardizations. It's globally recognized and used not only in manufacturing but also in sectors like oil and gas, pharma, utilities, and critical infrastructure worldwide. This makes it the common language of industrial cybersecurity, easing compliance and interoperability challenges. Lastly, it drives operational excellence by clearly defining the separation and interaction between systems. Organization achieve better manageability, smoother integration, and most efficient, resilient operations. Ultimately, the Purdue model is more than an architecture. It's a strategic foundation for secure, optimized, and future ready industrial operations. Congratulations if you have made it up to the last slide. So, as we wrap up, let's focus on how to actually implement the Purdue model to achieve real cybersecurity outcomes. In today's interconnected industrial environment, simply understanding the Purdue model is not enough. We need to put its principle into practice to defend against modern threats, ransomware, malware, and industrial cyber attacks that have potential to halt critical operations. So, what are the key steps for effective implementation? The first one is to deploy network segmentation in line with Purdue model level boundaries. By segmenting your network according to the model, you can create natural barriers that makes it harder for attacks to spread between business and operational systems. The next one is to implement defense in depth security control at each level, not just at the perimeter. Think firewall, intrusion detection, and access control tailored for every segment. Establish secure data flow control between zones to strictly manage and monitor any data that must cross boundaries. Conduct regular security assessment and compliance monitoring to catch vulnerabilities and ensure ongoing protection. Invest in employee training on industrial cybersecurity principles because this is very necessary to avoid any risk which comes through human intervention. And it is also very important so that they can follow and understand the importance of following the new protocols. So, here is the critical takeaway: the Purdue model is more than just a theoretical architecture, it's a practical, proven cybersecurity strategy. It enables digital transformation and advanced connectivity, while at the same time providing robust protection for your industrial operation against an increasingly sophisticated threat landscape. Implementing these strategies is essential not only to comply with standards but to protect your operation, business continuity, and reputation in this digital era. Thank you so much for watching this video.